Greetings and welcome to the Introduction to Astronomy. In this week's New Discoveries in Astronomy, we will look at listening to the expansion of the universe. So let's get started here. Astronomers can't agree on how fast the universe is expanding. What if the answer isn't in light at all, but in a faint, constant background hum? For decades, astronomers have tried to measure the expansion of the universe, and surprisingly, the answers don't agree. The mismatch is known as the Hubble tension, and now a new method may offer a way to resolve it by listening to gravitational waves instead of looking at light. There are two primary ways to measure how fast the universe is expanding. One looks at galaxies, nearby galaxies, tracking how fast they move away from us using light from exploding stars. The other looks much farther back, at the afterglow of the early universe, the cosmic microwave background. Both methods are precise, both are well tested, but they give different answers. Not by a small margin, by enough that both answers can't be right at the same time. Instead of relying on light, astronomers are now turning to gravitational waves, ripples in space-time produced by massive objects in motion. Across the universe, supermassive black holes are constantly merging. Each merger sends out gravitational waves. Individually, many of these signals are too faint or too distant to detect directly. But together they form a persistent background, a kind of cosmic hum. Not a single event, but a statistical signal built from countless sources. This is where the measurement becomes inference. Astronomers don't track individual events. Instead, they analyze the pattern of this background, its strength, its frequency distribution, and how it varies across the sky. These properties depend on how many black holes mergers occur over time, and how those events are spread across the history of the universe. And that distribution is shaped by one key factor: how fast the universe has been expanding. By modeling how expansion stretches and redshifts these signals, astronomers can work backward, inferring the expansion rate that best matches the observed background. In other words, the universe's expansion is encoded in the structure of the gravitational wave hum. It's not a refinement of existing methods. It's an entirely different way of measuring the same thing. It doesn't rely on stellar brightnesses, galaxy distances, or early universe radiation. It uses an entirely different kind of signal altogether. That makes it powerful. If this gravitational wave method agrees with one existing measurement, it could help resolve the Hubble tension. If it disagrees with both, it may point to new physics. Either way, it gives us a new way to test our understanding of the universe. We often think of astronomy as something that we see, but increasingly it's something we interpret. A faint background signal, spread across the universe, can carry information about its largest scale behavior. Not because we observe it directly, but because we've learned how to read what it encodes. The universe is not just visible, it's measurable through signals we are only beginning to understand. So that concludes this week's New Discoveries in Astronomy, looking at solving the universe's expansion mystery by gravitational waves. We'll be back again next week for another new discovery. So until then, have a great day, everyone, and I will see you in class.